Um, Now, the topic for discussion is life cycle assessment for carbon accounting. What is this life cycle assessment? The life cycle assessment is a methodology for accounting the carbon emissions. By carbon emissions, I mean all the greenhouse gas emissions. And the life cycle term denotes the emissions across the entire life cycle of the products, or for that matter, the entire life cycle of the processes and services. So, the purpose of life cycle analysis or life cycle assessment in carbon accounting could be to ensure that all the emissions, both the upstream and downstream, are accounted for, are counted. Okay, and the purpose is to make sure that the reporting, the policy decision, and the technology assessment is comprehensive. And if you want to compare one technology with the other or one service with the other, if you have a LCA of either of the two or both of the two, then that helps us enable fair comparison. Also, because it is a life cycle analysis, uh, this practice of moving one set of emissions to the other stage cannot be done, and that avoids the problem shifting phenomena, which is quite common in carbon footprint accounting. So, it gives you a reliable way of accounting the carbon. That is the meaning of this. Carbon accounting basically would then express the emissions in kgs of CO2 equivalent over the entire life cycle. There are various standards and protocols which are widely used in the carbon accounting, and those are ISO 14040, which is basically the very fundamental methodology for assessment of life cycle emissions. Then ISO 14044, this provides the guidelines for the LCA implementation and reporting. So one is about counting, and other is about reporting. Then there is a greenhouse gas protocol, which is a comprehensive standard for life cycle accounting, means measurement actually. And then there are assessment reports which are published by Intergovernmental Panel for Climate Change, which provides us the global warming potential values for different greenhouse gases. So in the LCA, the first step is to talk about the goal and define the scope. So clearly stating the purpose of the assessment is very important in your LCA analysis. For example, one statement of purpose could be like, we as an institution want to quantify the cradle to grave greenhouse gas emissions of an electric vehicle, and for that would lead to policy relevant carbon accounting. So here, when I set and when I write the definition properly and define the scope properly, you understand that three things are clear. Why are you doing this carbon accounting? So the target audience is policymakers, regulators, or it could be academics. Why for this study is done? This is to make sure that this analysis is disclosed to the public for intervention, and the purpose of doing this analysis is comparison of the various technologies, reporting, and then help us in design improvement. So if you define the goal properly in your LCA analysis, many things become clearer. The second thing in the LCA analysis is we talk about the functional unit. The functional unit could be mass based, especially if we are talking about products like 1 kg of steel produced, or it could be energy based if you are talking about energy values like 1 unit of electricity consumed, or if you are talking about transportation, it could be service based, 1 passenger kilometer traveled or 1 kilometer transported, and it could also be a lifetime based, that is 1 vehicle or so many kilometers of operation. So these are called as functional units. Now in your life cycle analysis, we would be talking about the lifetime emissions. So in lifetime emissions also, while talking about the lifetime emissions also, that could be either we talk from cradle to gate, cradle to grave, or cradle to cradle. Now these three terms are widely used in your reports. If you read the carbon accounting reports, one might find these terms often used. So for carbon accounting, from cradle to grave, we actually capture the complete environmental impact right from the raw material stage, including the processing of these raw materials, manufacturing to product, its use, and ultimately the disposal of that product. So that is the entire life cycle of the product is considered. Whereas more advanced feature is cradle to cradle, wherein we talk about a circular loop or circular economy, wherein we also include the recycling and reuse of the products. So this system boundary has to be clearly defined when we do for carbon accounting. Are we doing the analysis from cradle to grave, or cradle to gate, or from cradle to cradle? The other important thing in the LC analysis is the cutoff criteria. So the cutoff criteria would specify which processes or which materials would be excluded from the analysis or from the assessment. This ensures that there is a practical implementation without losing the scientific rigor. So one might include some materials which have a very negligible content. For example, I might neglect the materials which have a total contribution of only 1 to 2% of the total mass, or the materials which contribute negligibly to the energy content, or the processes I could neglect which are not contributing much to the CO2 emissions, or the infrastructure which have a minimal contribution. So writing this clearly in the report, in the LC analysis, that is called as the cutoff criteria. Then comes the inventory part. So this inventory analysis is very important because it is data intensive, and it is a core, it is a central part of the carbon accounting thing, where all the inputs and all the outputs are quantified across the product's life cycle. So for that, in your LC analysis, we draw a process flow diagram. So that process flow diagram, if you are able to draw properly, mapping all the inputs, then it is easier for quantifying the emissions. Collecting the data accurately in a detailed manner on the material flows, on the energy which is being consumed, on the emissions which occurred because of transportation and enduring and the various industrial processes, both the primary sources as well as secondary sources, if they are collected accurately and tabulated in the activity data, that becomes important in the LC analysis. And correct choice of emission factor is extremely important, and that could come from various scientific reports, could be international like IPCC, or it could be some national database. But that emission factor is critical in your life cycle assessment. And then finally, allocation of these emissions when the multiple products are produced using the energy analysis, mass analysis, as well as on the economic basis, that has to be done in your analysis, life cycle analysis. When we talk about the activity data collection, the activity data collection examples are tabulated here. Like in material flows, I would be interested in knowing how many kgs of steel or plastic or aluminum or glass is used, and how much energy is being consumed. Could be electricity, could be the primary energy. The primary energy we generally report it in joules, megajoules, kilojoules, so on, and electricity we report it in kilowatt hour. Kilowatt hour means units of electricity. The transportation we refer to ton kilometer, that is both the mass as well as the distance traveled, and specify whether it is traveled by road, by rail, by air, by sea, and so on. And on the process emissions, we would be interested in knowing the emissions right from carbon dioxide, methane, nitrous oxide, and so on. The data could be measured directly during audit, that is primary data, or it could be obtained from the literature, the company's data, or from the literature, that is secondary data. Next comes the calculation of emission factor and the computation of emissions. So as I said, emissions is simply a multiplication of activity data into emission factor, and for that emission factor, trusted sources are to be used, including the sources published by national databases or by IPCC. In the allocation, because multiple products are produced from a single source in some cases, or from a single process, then we need to allot the emissions fairly. So this fair allocation could be on the mass basis, could be on the energy basis, could be on the economic basis, or on the system basis. So this, what allocation method one uses, has to be clearly stated in the final report. And then once you do this, we get the final life cycle impact assessment, wherein we focus on the climate change category. You know that different greenhouse gases, they contribute to global warming in different ways. And many gases, they have the warming potential which is many times that of CO2. For example, methane would have a global warming potential 27 times that of CO2, whereas nitrous oxides would have the contribution to global warming 273 times that of CO2. So that is useful when you convert it to CO2 equivalent. So CO2 equivalent is, the formula is given here, the summation of Mi into global warming potential of that ith atom, that is ith gas. Okay. And then comes the important part in your life cycle analysis, which is the calculation process, wherein the upstream emissions, the downstream emissions, as well as emissions during the core processes are to be captured. So for that, a detailed understanding of the process is very important. Understanding of what raw materials are used, how carbon intensive it is to extract the raw materials, how they are processed and transported to the manufacturing site, and during processing and transportation of these materials upstream to the manufacturing site, what are the emissions involved, and then once it arrives in the factory, during the core process, what are the emissions during manufacturing, during assembly, during packaging and distribution. That would be the core emissions. And then finally, when the product is taken to use over the entire life up to its disposal, what are the emissions. So this is the aggregate emissions over the life cycle, which would determine the total carbon footprint and generally expressed in kgs of CO2 equivalent. Once this report is ready, we go for interpretation and analysis, which we'll discuss in the next part of our lecture.